We've talked so far about measures of central tendency and measures of location, as well as measures of variability for a numerical variable. However, sometimes you also want to examine the data for a numerical variable visually. You want to see what it looks like. You want to see what the distribution looks like. Especially when you're looking at measures of spread, it's very useful to see how spread out a set of observations can be. So let's go to this example of life expectancy. Suppose you're an epidemiologist or somebody working in public health, and you want to examine life expectancy across countries. Why do people in some countries live longer than people in other countries? And how spread out is life expectancy across countries? What's the typical life expectancy if you just take all these countries together? So a first analysis will entail some kind of visualization of the central tendency for life expectancy and this distribution of life expectancy for these different countries. And a sort of a further analysis would entail examining the spread of life expectancy across countries. So for these kinds of questions, when you're looking at a measure of central tendency and a measure of spread, visualization is often extremely helpful. So let's look at our data set for this epidemiological analysis of life expectancy. So you have this set of observations, and you have these different variables. The first variable, that first column, is country. It's the name of the country. Then you have this variable representing the population growth in percent. So some countries on a yearly basis have a higher level of population growth, and some countries have a lower level of population growth. You also have this variable for life expectancy in years. That's how people are living in these different countries in terms of how long they're living. And then you have this variable for the gross national product per capita. The gross national product per capita is a measure of the overall economic development for that particular country, especially when you're looking at public health studies. Gross national product per capita, a level of economic development, is often a very important factor in understanding variation in terms of life expectancy and other health outcomes across countries. So let's focus now on life expectancy in particular. A first analysis might entail the construction of what's called a dot plot. So here's a dot plot of life expectancy in our data set. In a dot plot, typically you use one dot for each observation. So here we have a set of countries, and each dot is a different country. Each dot is a different data point or observation. And then on the y-axis, on that vertical axis, we have the frequency, the number of counts, the number of observations or data points for each value of life expectancy. So you can see here that a lot of countries, there's some clustering in terms of life expectancy, but there's some variation as well. One issue with a dot plot is that it can be messy with large data sets because you're plotting each observation, each data point. If you have a large data set with many observations, let's say you have a data set of 1 million people, a dot plot will be very messy because you have too many data points to put on one graph. So let's look at this dot plot of life expectancy. You can see that most countries, they're kind of in the upper 60s and mid 70s. So most countries, there's some kind of clustering around the typical life expectancy in our set of observations. But we do have this outlier. This outlier here is Haiti. It's a bit lower than average in terms of life expectancy. In fact, it's the only country in our set of countries to have a life expectancy below 60 years. So you can see a dot plot. It can be quite useful for understanding the center part of a distribution, the spread, but also whether or not there are outliers. In this case, in our data set, Haiti seems to be an outlier. It's an extreme value. It has a lower life expectancy than most of the other countries in our data set. Another useful sort of plot for a numerical variable is something called a stem and leaf plot. It really is based on a list of our data. So in a stem and leaf plot, you have stems and leaves, right? The numbers to the left of a vertical bar is called the stems, and then the digits to the right we call leaves. all the stems that begin with the same digit and the corresponding leaves are written beside each other, and this allows you to reconstruct each observation in a set of observations. You just use the stem and the leaf to reconstruct the actual values of the data points. So here's a stem and leaf plot for our set of countries. Each observation has its own number. And you can see that there's this vertical bar. So the numbers to the left of this vertical bar, those are the stems. And then the numbers to the right of this vertical bar, those are called leaves. Now, usually a stem and leaf plot will identify what distinguishes a stem from a leaf. In this case, the stem is the leading value of our number, and then the leaf is really in the ones place. So for example, in this data set, it's all these sort of integers. It's these counting numbers, 54, 56, 78, 80. There aren't decimal places. So in our data set, the lowest life expectancy is 54 years. That's just a reconstruction of the observation based on the stem of 5 and the leaf of 4. The highest life expectancy in our data set is 79. That's because the stem is 7 and the leaf is 9. So you can see that from a stem and leaf plot, we have an instant snapshot of what the maximum and minimum values are. In fact, you could even construct a range based on a stem and leaf plot. We also know that, for example, 5 countries have a life expectancy of 75. So you can see that each leaf is a different observation. It's a different data point. And to reconstruct that observation or data point, you use the value of the stem. So we have 75, 75, and so on and so forth. We have these 5 countries with a life expectancy each of 75. And one thing about a stem and leaf plot, which is a similar problem with a dot plot, is that because all observations, all data points are represented in a stem and leaf plot, it really only works for small data sets. It can be impractical for even a modestly sized data set. In our case, we have a set of countries. So the number of observations is pretty small. But if you have a data set of 1 million people or 10,000 or even 500 people, which is actually quite common in survey research. In the social sciences and humanities, a data set of 500 observations of 500 people is pretty common. A stem and leaf plot can be really messy and difficult to work with. It can create too much visual clutter. But if you subset your sample or your population to a smaller set of observations, a stem and leaf plot can be very useful. Or if you have a data set with a relatively small number of observations. For example, in psychology, our data sets typically are a little bit smaller, so stem and leaf plot can be quite useful. If you have a lot of observations and you want to look at the distribution of a numerical variable, histograms are often very useful. They show the number of data points or the density of data points within a given interval. So you can bin a numerical variable based on intervals that really reduce the number of data points that you really are representing in your histogram or in your plot. In a histogram, each bar covers an interval, also known as a bin, and the height of each bar is equal to the number of observations in that interval or bin. So a histogram is very commonly used because since you're not plotting all the observations, all the data points, it works with data sets of all sizes, from a very small data set to a very large data set. And that's because you can alter the number of bins depending on the granularity of the visualization that you really want. So here's a histogram of life expectancy in our data set. You can see that it looks similar to the dot plot or to the stem and leaf plot in the sense that you see a lot of observations in the upper 60s and lower 70s. And you do see some kind of spread, especially in the lower end, and that the lower bar, that first bar that's really small, that reflects that one data point of Haiti, which is kind of lower than all the other observations in terms of life expectancy. But one thing about a histogram is that how you represent the data, it depends on the number of intervals or the number of bins. So in one case, we have a histogram of our data with 3 bins, and in another case, we have a histogram with 10 bins. You can alter the number of bins, and that will give you an idea of how the data are distributed based on a level of granularity, either very high with a high number of bins or a sort of low level granularity with a few number of bins. That is sort of one issue with the histogram, though, because it can be misleading. If you have a lot of sort of variation in the data, if you have like multiple sort of peaks in the data, that can be hidden if you have an overly sort of small number of bins. If you have few bins, it can really mask a lot of the interesting information in a set of data. An alternative to the histogram is something called a density plot. It is similar to a histogram, but it smooths out the number of bins. Conceptually, you can think of a density plot. It's like a histogram, but a histogram with very, very small bins, so small that you just kind of have a smooth line, a curve fit over the data points. The height of a density plot, it gives an idea of where the observations, the data points are concentrated. So here's our data set of life expectancy. Instead of a histogram, instead of bins, you have this smooth curve, this line that represents, it's similar to histogram if you have very, very, very small bins. In a density plot, because the smoothness of the curve can be misleading, we also often present what's known as a rug of data points. This rug shows all the actual observations, and the points are kind of jittered around randomly in the vertical axis to kind of avoid overplotting, over the overlaying of data points. And that rug gives you an idea of where the data points are concentrated. So you can see that there are a lot of data points around that sort of big hump, but then there aren't very many observations in that tail. And that tail really only has one observation, and that's Haiti. So the whole point of the rug is to remind the reader or the person who is creating the graph or trying to interpret the graph that a density plot different areas under the curve are based on a different number of observations or data points, and we shouldn't be too hasty to extrapolate or to make conclusions based on a part of the distribution that is based only on a handful of data points. So you can see there are a lot of data points around the middle part of the density plot. There's really only Haiti at the lower end. An alternative to the density plot in the histogram is something called a box plot. You will see a box plot used a great deal in a lot of research when you're trying to understand the distribution of a numerical variable. Boxplot is sometimes also known as a box and whisker plot. That's because you have a box and then you have these two things called whiskers sticking outside of the box. The middle box in a box plot is based on the median, or the 50th percentile, and the first and third quartiles. The lower whisker is based on the first quartile and as well as the interquartile range. You basically take the first quartile and you subtract 1.5 times the interquartile range. The upper whisker is based on the third quartile as well as the interquartile range. And what you do is you take the third quartile and you add 1.5 times the interquartile range. So a box plot is really based on quartiles and the measures that are based on the quartiles, which are the median and the interquartile range. So let's look at this a little bit more in depth. In a box plot, the median is given by a dot in the middle of a box. Sometimes it's a vertical line, but in this case, it's a dot. That gives us the location of the median. So that's the 50th percentile. We know that 50% of the observations lie above that value and 50% of the observations lie below that value. The two edges of the box in a box plot give us the first quartile and the third quartile. So we know that the middle 50% of the data, it lies within those two edges of that box in a box plot. Then we have these two whiskers. Right? The lower whisker is the minimum observation that is not an outlier, and the upper whisker is the maximum observation that is not an outlier. Then we have any sort of observations beyond the whiskers. Those are outliers. Those are extreme values. So in this case, we have one outlier on the lower end, and that's Haiti. As we also, when we looked at histograms and density plots, we noticed that Haiti was an outlier. In this data set, we don't have any outliers on the upper end. Right? So the only outlier we have in comparison to the rest of the data is on the lower end. But what is an outlier? There is no one rule for detecting an outlier. In a box plot, we have a particular way of understanding what an outlier means. Outliers are very important when we are doing research because they can help identify data that might be erroneously recorded, so we might have a mistake. The other important point about outliers, the reason why we're so interested in them, is that they can affect our summaries of data. So the sample mean, the standard deviation, the variance, all of these are sensitive to an extreme value, to an outlier in our data set. So identifying outliers is very important when we're trying to understand a set of data. The key point is that we want to make sure that these measures are not misleading us. So one commonly used measure for finding an outlier is something known as the Boxplot Rule. Because there is no one hard and fast rule for identifying outliers, a lot of people have kind of coalesced around this idea of the Boxplot Rule. The idea is that a value is an outlier if it is less than the first quartile minus 1.5 times the interquartile range, or greater than the third quartile plus 1.5 times the interquartile range. So when you look at a box plot, the lower whisker of a box plot, it's that minimum observation that is not an outlier. Then the upper whisker is the maximum observation. It's the maximum value of an observation that is not an outlier. So let's look at our set of countries. We only have one observation that is less than the first quartile minus 1.5 times the interquartile range. And we have no observations that are more than the third quartile plus 1.5 times the interquartile range. So based on the box plot rule, we have one outlier in our set of observations. A related concept to the idea of outliers is skewness. The difference between what an outlier is and what a skewed distribution is, it's not that different. You can kind of think of as a skewed distribution has a lot of outliers. In either case, whether you have skewness or outliers, a numerical summary, such as the mean, standard deviation, or variance, it can be very misleading. We like to talk about distributions in terms of being symmetric, left skewed, or right skewed. One key point about skewness is that the skew, it's referring to the direction of the tail. So these are three different distributions with different kinds of skewness. You can think of skewness as kind of where sort of a lot of outliers are located. So a distribution that is symmetric, you have sort of outlying values or on both ends of the distribution, or you might have no outlying values. But the key point is that in a symmetric distribution, there is no skewness. And in a symmetric distribution, in general, the mean, the median, and the mode, they tend to be very similar. In a distribution that's skewed left, you have a tail that's skewed to the left. What generally happens is that the mean is pulled out in the direction of those extreme values in the tail. In a distribution that is skewed right, in general, the mean is pulled out in the direction of those outlying values. So we like to talk about a distribution as being skewed left, skewed right, or symmetric. In a similar way, we like to talk about the different modalities of distributions. So in the case when we're just talking about skewness, we were looking at distributions that all had one peak. But what happens if a distribution has multiple peaks? If there's one clearly defined peak, we say it's unimodal. If there are two peaks, then we say it's bimodal. And if there are three peaks, we like to say it's multimodal. Now, when we talk about whether a distribution is bimodal, unimodal, or multimodal, that is not the same as talking about what a numerical summary of a mode means, meaning a distribution might have two peaks, yet it might have one numerical mode. So when we talk about whether a distribution is one mode, two modes, three modes, where we're talking about the sort of apparent peaks in a distribution. We're not talking about the exact numerical summary, because in general, a set of observations will have one mode. But if you really understand and look at the distribution from a visual sense, it's quite clear that there might be two apparent distributions overlaid on top of each other. There might be two peaks. And so that's why we say if you kind of separate out these two distributions, they're really two modes. If you treat the one distribution as really two different distributions. So let's look at these distributions in terms of life expectancy and our other variables. The distribution of life expectancy, it's left skewed because of Haiti. that one value of Haiti, it's sort of skewing the mean downwards. To put it another way, the mean is being pulled out relative to the 50th percentile or median. This is why the mean can be misleading as a sort of snapshot summary of the typical life expectancy in our data set. This distribution, however, is unimodal, meaning most of the observations kind of have one, the overall distribution, there's one peak. Most countries are in the upper 60s and lower 70s in terms of life expectancy. But in our data set, we also have this variable of gross national product per capita. This gives you an idea of the total level of economic development for these different countries. For this variable, the distribution is right skewed, meaning we have a lot of observations that have a relatively low level of gross national product per capita, but then some countries are really quite rich in terms of overall economic development. And those extreme values, we'd expect the mean to be pulled upwards. That's because the distribution is skewed right. So the mean is going to be higher than the median, or 50th percentile. This distribution, it's slightly bimodal. It's clear that there's really one mode if you look at the distribution as a whole, but there are two peaks, so we like to say it is bimodal. If we look at the distribution of population growth in our data set, it's roughly symmetric. There is some right skew, so we'd expect that the mean might be a little bit higher than the median, but not substantially so. And then you can also see the distribution is slightly bimodal. There's one really obvious peak, so there's one numerical mode, but there's sort of a smaller hump near the middle to high end of population growth percentage. Things to know for this week in terms of visualizing numerical data. Dot plots, stem and leaf plots, histograms, density plots, and box plots are all used to visualize numerical variables. We don't use bar graphs or pie graphs to look at numerical data. We use these kinds of plots that we just discussed. Especially when you have larger data sets, we use histograms or density plots or box plots. Dot plots and stem and leaf plots are better suited for smaller data sets where we have a smaller number of observations. Box plots are very commonly used, and they're extremely helpful for identifying extreme values or outliers in a set of observations for a numerical variable. We use something called the Boxplot Rule to identify outliers. It's not the only rule for identifying what an outlier might be, but it's a very commonly used rule. Distributions in general, we like to characterize as right skewed, left skewed, or symmetric. And distributions are often also described as unimodal, bimodal, or multimodal. So with that, that really ends our discussion this week of how to visualize numerical data.